Chapter 9, Problem 13. Find the tension in the two wires supporting the traffic light shown in figure 9-53. So here's our figure, 53 degrees off the horizontal on the left, 37 on the right of the junction that holds up the light, and the light weighs, well, the stoplight's mass is 33 kilograms, and it will feel a weight of that multiplied by G, right? So the goal is to find basically the tension, T1 and T2. So you can name those either way, T1 and T2, whichever you prefer. But this can be a very simple problem depending on where we choose our center of mass, let's say, should be. You might be tempted to look at the light as the point of mass, but then you would have to only include the tension, and it would just be a point mass like this, a tension like this, and mg, and this is just not enough information, right? We want to have both. We want to have both of these tensions. We don't only care about x, right? So the general form of what we want to do is going to be put the center of mass here where the dot is, so that we could have a free body diagram with simply T1, T2, and mg. And then when we have this, what we can do, since we know some quantities, we can start to break T1 into components and break T2 into components, x and y components. So this will be x and this will be y, right? So both y's are positive, but the x's flip across the x-axis. Well, the tensions flip across the x-axis. But this allows us essentially to add up the forces, and we can use the equilibrium condition also to our advantage, that when we talk about the sum of the forces, Newton's second law says that this is equal to ma, but since the traffic light's not moving, this is equal to 0. So this allows us to, well, yeah, like I said, you want to draw a free body diagram similar to what I had before. And I just call the angles different names instead of the numbers, so I could write them less. But you should always remember that here, that on the left angle is 53, and then the right angle is 37. There. But yeah, so similar angles tells me that the triangle, if you look at the two horizontal lines, one right here and one right here, the angle is going to be the same. This angle is going to be the same. That is just a geometric rule that you should know. The same goes for the other side, here and here. But yeah, that helps us to make this triangle. And once you've made this triangle, then you can really split up the components like we have here with cosines and sines, and then start to do some calculations. So sum of the forces. Here we can sum the forces in the x direction. And it turns out that the only two that we see are the T1 x component and the T2 x component here and here, right? So they don't quite cancel each other out because they have different values, but they do equal each other. Let's say, and then let's say we can get this relation here. T2 is equal to T1 times cosine phi over cosine theta. So this is really just a number. So T2 is equal to some number multiplied by T1, but I just didn't do the calculation here. So you can easily put in cosine 35 over cosine 53, and you should find out what this number, circled number, is. But for now, I'm not going to focus on it. The next page, we want to sum the forces in the y direction. So this one's a little bit more. We have gravity to include as well as the tensions. And so since it's y, we're going to be using sine. And we end up with the second line, T1 sine phi plus T2 sine theta minus mg is equal to 0. And since we have a relation from page 3 about tension 2, we can plug that in here using the page 3 T2 relation. And then we can solve just for T1. So we just plug this in, and if we multiply, actually, if we notice here, there's a sine over a cosine theta. It's actually equal to tangent theta, right? So we can just call this T1 cos phi tangent theta minus mg. And then the next page should have our, so like I said, the tangent theta is here. So you can factor out T1 and then divide to get your first tension, and that's going to be about 195 newtons, a little bit less. And then you can just plug that number into the original equation from page 3, because because like I said, this stuff just a number, and since we just found this as to be 195, we can just multiply them and find T2, which turns out to be about 260.